I welcome you all in this presentation related with the subject materials processing fundamentals and practical, and we are talking about the welding of metals. So, in this particular presentation I will be talking about the heat affected zone of the work hardening metals and precipitation hardening metals. Okay. Work hardening metals are those metals which are strengthened through the strain hardening, means through the controlled plastic deformation. The number of dislocations are increased, which in turn helps to enhance the yield strength and hardness of the material, but certainly at the cost of the ductility and toughness. On the other hand, precipitation hardening metals are those in which the fine precipitates are developed through the suitable heat treatment like T6 or T4 heat treatment, and these fine precipitates help in increasing the strength of the material. Okay. So, during the welding, when heat is applied, the dislocations and these fine precipitates both are very adversely affected. Okay. And that in turn results in the development of a heat affected zone, which is usually weaker in terms of the strength and the hardness, and that is why mostly during the welding of the work hardening metals and precipitation hardening metals, we find the HZ softening. Okay. So, we will try to see about this aspect little in greater detail, apart from the kind of microstructural changes that are observed in the during the welding of the work hardening and precipitation hardening metals. Okay. So, starting with this weld thermal cycle, so content, as far as content is concerned, the effect of weld thermal cycle, especially the peak temperature, soaking time and the cooling rate. Okay. So, in case of the precipitation and work hardening metals, probably the cooling rate does not affect the things much, but certainly the role of the peak temperature and soaking time is really great. Okay. Because the relevant phase transformations, solid state phase transformations are very limited during the cooling stage. So, precipitation hardening metal and the work hardening metal. So, like say in precipitation hardening metals, these can be like stainless steels, PH steels is one, and many copper and titanium and alloys, aluminum alloys. So, all these are the say precipitation hardening metals, where the strength, say yield strength, is realized by developing fine precipitates in these metals. Okay. And these fine well distributed precipitates effectively hinder the movement of dislocations, through which the plastic deformation will be facilitated. So, if the movement of dislocations is hindered through these precipitates, then yield strength of the material is enhanced. That is the mechanism. So, higher the fine precipitates in increasing percentage or area fraction will be resulting in the increased yield strength, increased hardness of the material. Okay. So, this is about the pH metals. What is done for for the precipitation hardening purpose, like say relevant precipitation hardening metal is taken and it is heated to the high temperature. So, this is the heating phase. So, we have temperature in the y axis and time in the x axis. So, the kind of thermal cycle which is used for the precipitation development of the precipitates, hardening precipitates in the pH metals, about that I am talking right now. So, here heating, then soaking. Okay. So, this soaking allows the formation of the homogeneous solid solution, wherein all alloying elements will be getting dissolved. Okay. And once this is formed, then it is quenched rapidly. So, quenching is done as a, so first stage heating and then quenching. Okay. So, this can also be termed as solutionizing, then quenching. Quenching helps in development of the supersaturated solid solution. Okay. Once it is quenched, we get the supersaturated solid solution. Okay. Then we have two options. One, this supersaturated solid solution having the alloying elements greater than their solubility limit, then that is left at room temperature for longer time for realizing the natural aging. Okay. So, this is done through the T4 heat treatment, and when it is reheated to the higher temperature, okay, say 150 to 200 degrees centigrade, say in case of the aluminum alloys, then during this reheating the precipitation will be happening at much faster rate, and the peak hardening is realized much earlier or quickly faster. So, here you can see that this is the termed as T6 heat treatment, where the reheating is done through the artificial aging instead of the natural aging at the room temperature. So, how long at a high temperature the component which is supersaturated solids in supersaturated solid solution state is. So, for that what we have to do? We have to see that the hardness as a function of the time for different holding temperatures, like say we get this kind of thing. So, here low temperature say 120 degrees centigrade or high temperature 150 degrees centigrade. When soaking is done during the T6 heat treatment for artificial aging, so we will be attaining the peak hardness, peak strength much earlier as compared to the case when the low temperature aging means T6 heat treatment artificial aging is done at a lower temperature. So, this state when the alloy gets the maximum strength is known as peak hardened condition, hardened condition, okay. And this will be happening when it has produced the maximum number of the desired type of fine precipitates in the metal, okay. If we see, so there is an optima, otherwise on the either side we have the lesser hardness. So, the if we see on the left side of the maximum hardness, this is the under aged state. Under aged state means the material has not hardened to the peak hardness level and still the hardening is going on, and over during the and after the peak hardening, if further high temperature is maintained for longer time, then we will be getting the over aged state, okay. In the over aging, during the over aging again hardness or strength starts coming down, okay. So, what happens when the pH metals, when these are subject to the welding, say fusion welding or solid state welding, so heat affects these precipitates, okay. So, about the effect of in a metal which has been hardened, peak hardened or hardened through the under aging or over aging, will be having some kind of precipitates. In case of under aging, the number of precipitates will be fewer, and in case of over aging, these will be coarser and fewer, okay. That is the only difference. So, now when this kind of the systems, when these are subjected to the welding, then how the heat will be affecting to these metals. So, say metal, say aluminum alloy like 6061 in the peak hardened condition, when these are subjected to the welding, what happens to? So, application of the heat during the welding, again just like in normal weld thermal cycle, the zones which are next to the fusion boundary, they will be experiencing much higher peak temperature as compared to the zones which are located away. Like say in this case there are 3 locations 1, 2, 3. So, obviously the maximum temperature will be attained at location 1, location 2 somewhat lesser, and further lesser temperature at the location 3, okay. So, we know that when this kind of the metal system, so this is about the peak temperature, and in the same way soaking time will be maximum for the location 1, soaking time will be lesser for location 2, and soaking time will be further lesser for the 3. So, both peak temperature and soaking time, these will be decreasing with the increasing distance from the fusion boundary. So, soaking time at location 1 and peak temperature at location 1 is higher than the soaking time and peak temperature at location 2 is lesser, and then peak temperature and soaking time at location 3 further. So, this is minimum, okay. And these are the two most important aspects, peak temperature and soaking time are the two most important aspects that will be affecting these two types of metals, precipitation hardening and work hardening metals. Okay. So, this is one aspect. So, another aspect is what? Let us take a metal in annealed condition. Okay. Metal in annealed condition. Metal in annealed condition will not have any kind of the dislocations between, because it will be having the complete recovery state, means even if the dislocations were there, these will get annihilated perfectly. Okay. So, when this kind of the metal is subjected to the plastic deformation, okay, so it induces lot of dislocations. These dislocations, what they do? These induce the strain field wherever they are present, and this in turn interferes with the movement of dislocations. Okay. So, if the one dislocation is moving, then the other dislocations will be interfering with the movement of the moving dislocation, and that in turn will make the deformation difficult due to the increased resistance to the movement of dislocations. Okay. So, this is the material when the plastic deformation state. If we deform less, then the number of dislocations that they will be fewer. If we deform more, these numbers will increase, and accordingly if we see increasing plastic deformation will be increasing the hardness, increasing the yield strength, primarily due to the increased dislocation density. Okay. So, increased dislocation density, increased hardness and yield strength, and due to the plastic deformation. Okay. So, what happens when these kind of the systems are heated during the welding? Say this is the metal having large number of dislocations, high dislocation density like this, right. And so, when heat is applied during the welding, the zones, all the zones which are heated to the higher temperature where recovery can occur, they will be experiencing the loss of dislocations. Okay. Because during the recovery, these dislocations will annihilate. So, higher the temperature, faster will be the recovery, and annihilation will be more significant, annihilation of dislocations will be more significant. So, what will happen here? Away from the fusion boundary, dislocations may not be affected, but those zones which are being heated to the higher temperature, so there may be partial recovery, and the recovery may be complete in the zones which are being heated to the too high temperature. So, there may be partial recovery, there may be, so next to the fusion boundary there may be complete recovery, partial recovery, and there may be unaffected base metal. This is about just the work hardening metal aspect. Okay. But if the high temperature is maintained for a longer time, in any case we are going to have the coarse grained structure. So, we will have the coarse grained structure which is free from any kind of dislocations. So, there are two aspects, one grain coarsening and the loss of dislocations leading to the dislocation free zone formation. Both these aspects are going to reduce the hardness significantly as compared to the locations which are away from the fusion boundary. Okay. So, if the location is away from the fusion boundary, then there the recovery will be partial, means the loss of hardness, loss of strength will be partial. Okay. So, therefore, considering this, we have the say three zones. One is the coarse grained complete recovery zone, okay, like this, right. So, here hardness will be minimum. Then there is a partial recovery zone. So, their hardness will be increasing little bit, then unaffected zone. So, base metal will remain unaffected, will be showing the higher hardness. This is the partial recovery, and this is the complete recovery and coarse grained zone. Okay. This is how we can see the way by which weld thermal cycle be affecting to the work hardening metals. Okay. So, as we have already talked about the weld thermal cycle, during the welding along the weld center line, different locations experience the different temperatures, and this temperature will be changing as a function of time, and there are three parameters: peak temperature, soaking time and cooling rate. For the work hardening and precipitation hardening metals, these two are extremely important. If the other mechanisms like transformation hardening is not working significantly. Okay. Then because of these kind of the temperatures which are observed, higher peak temperature, longer soaking time, okay, longer soaking time, this zone. So, because of this we get very coarse grained HZ, okay, and then we find a zone which is a complete. So, in work hardening metals there is a recovery, recrystallization and grain growth. So, zones which are next to the fusion boundary, they will be experiencing huge grain growth and recrystallization and recovery. Okay. But if we talk of the pH metals, in pH metals there will be grain growth, there will be reversion, that is a loss of precipitates, because precipitates will get dissolved and the overaging. Okay. So, they will get coarsened. Okay. So, if we see, so about these aspects we will be talking little in more detail. Okay. So, let us say work hardening metals. In work hardening metals, as I have explained, say the work hardening metals, this has a lot of dislocations in an affected base metal. So, if this is the fusion boundary, okay, this is the fusion boundary. So, if we talk of the zone 1, this will be experiencing much higher temperature, much higher cooling rate. If we talk of zone 2, a little lesser cooling rate and lesser peak temperature, like 3 for 3 and 4. Okay. So, it's zone 1, zone 2, zone 3 and zone 4. So, zone 1 is in the, like say this, so these are the, this zone which is completely free from the dislocation. So, this is complete recovery is there, then the partial recovery, then unaffected base metal, then there is zone depending upon the kind of the alloy that we are dealing with. If it is having a solidification temperature range, then it will be producing a partial melting zone. Okay, where there we will have both liquid and solid phases. In the weld zone particularly we will have the metal which has been heated above the liquidus temperature. So, in this case if we see, the hardness distribution, if we try to see for this kind of the metal system, then in the base metal, like say along this line, if we see, the hardness will remain high until there is no effect on the dislocation density. Okay. But then in the partial recovery zone, hardness will start coming down. Okay. Then further it will be minimized. Okay. Then the partial melting zone. So, this is the recovery, complete recovery zone, then the partial recovery zone, and then the, so apart from this, this zone next to the partial melting zone will be very coarse grained HZ. Okay. And why it is being formed? Because higher temperature is being maintained for longer time. That is what in turn will be leading to the complete recovery as well as the grain coarsening. Okay. Then there are other zones which are heated, then they will also be experiencing the recrystallization and grain growth. We know that when a metal is in the deformed state, okay, so initially the recovery takes place, followed by the recrystallization, and then if further higher temperature is maintained, then it will be experiencing the grain growth. This is applicable for all kind of the metals, okay, whether it is transformation hardening, work hardening or the precipitation hardening metals. Okay. And because of this, what we find mostly in fusion welding, see the kind of the weld metal that we can produce, that is in our hand, because we can choose the filler as per our need and we can develop the weld metal as per our requirement. But the zones which are getting coarsened, forming the coarse grained structure, complete recovery is taking place, they are going to show significant softening, hardness is significantly reduced, then the partial recovery and the base metal. Okay. So, this is the partial recovery zone, this is the complete recovery zone, and where the grain coarsening is also taking place. So, in these areas hardness will be minimum, and this is why it is known, this will be leading to the HAZ softening. HAZ becomes very weak, and if in this scenario if you make a weld like this, okay, so here both the sides there will be coarse grained heat affected zone, okay, that will be producing the recovery, complete recovery, also coarse grains and complete recovery zone. So, this will is going to have very low hardness. So, if we try to measure the hardness distribution across this line, then what will happen? The weld hardness is in our hands, that we can, that is what we can control. Then both the sides will have this zone, okay. This is the weld, then both the sides there will be two soft zones in form of heat affected zone, and this the minimum hardness zone usually becomes the location of the weakness, a location of fracture, and this is primarily attributed to the complete recovery and coarse grain structure in the work hardening metals. Okay. As I have said, in the case of the precipitation hardening metals, strength is realized through the development of precipitates. Okay. So, in the case of base metal, say these are fine precipitates well distributed in the base metal, and which in turn will be resulting in the higher hardness and higher strength. Okay. And this is the weld metal which can be made as per the weld metal can be developed as per the requirement of the desired strength and the hardness. But what about the heat affected zone? If we see the heat affected zone, so this zone, if we see this zone which is in the two phase zone, okay. So, this is an, like say this is an alloy having the partial solid solubility. Okay. So, in this case, if we see this for this particular composition of alloy, this is the mushy zone temperature between the liquidus and solidus. Okay. So, the zone which is being heated in this temperature range, that will be developing the mushy zone, two phase zone, where both liquid and solid will be present. Okay. Next to that, we will have the zone which will be heated to the too high temperature, like this. In this band is the single phase zone. So, if there is any precipitate, that will get dissolved, or if there are few are left, then they will get coarsened like anything, and that is what we can see. The precipitates which are being heated above this the solvus line. So, these are like the different lines showing the solvus lines for the different types of the precipitates. When we heat the system, the different precipitates will be getting dissolved, and then they will be forming the homogeneous solid solution. Okay. So, on heating, the dissolution of the precipitate is one of the most important aspects. Since we get the various types of the precipitates depending upon the kind of alloy, these precipitates will get destabilized, decomposed and dissolved on heating above the different temperatures. Say one type of precipitates, okay, second type of precipitate. So, the different precipitates will get dissolved at different temperatures, it is fine, but since the temperature being attained by the zones next to the fusion boundary is much higher, therefore, what will happen, everything, all precipitates are going to get dissolved. Okay. So, we will find the precipitate free zone, okay, and this formation, this dissolution or decomposition of the precipitate is called reversion. Okay. This will be, once the complete reversion takes place, then the precipitate free zone will be formed. Since these metals are strengthened through the development of the precipitates, and if these are getting dissolved during the welding, then certainly significant softening is going to take place in this zone where the precipitates have been dissolved completely, reversion has taken place. Then there will be a zone where, due to the somewhat lesser peak temperature, the another zone somewhat lesser peak temperature, the dissolution of the precipitate is somewhat limited, but still coarsening is taking place. Okay. So, partial dissolution is the another, there is another zone where dissolution will be partial and little coarsening. Okay. So, and here complete dissolution next to the fusion boundary, complete dissolution and significant coarsening if anything is there, and coarsening. So, the complete dissolution or significant coarsening of the left out precipitates will be causing the significant weakening. Okay. And in the zones little away from the fusion boundary, that will be causing the partial dissolution and little coarsening. So, there will be partial loss of strength as well as the hardness. Okay, that is why we will see little higher hardness. So, we will see the H1 is the minimum hardness, H2 little higher hardness, and H3 maximum hardness. H3 is a zone where we have precipitates, there is no loss of the precipitates have taken place. If we consider the complete reversion zone is in zone 1, partial reversion zone is the zone 2, and an unaffected base metal is the zone 3. Okay. So, it will have the maximum hardness. So, H1 minimum, H2 somewhat greater, and maximum hardness for H3 zone, and this is primarily happening due to the different thermal cycles being experienced by the pH metals during the welding. Like say, this is just an example. If we see during the solid state joining like friction welding, where one component, one end is fixed, okay, another end is rotated in frictional contact with each other. So, here generates the frictional heat and coupled with the plastic deformation, and at the end we get the component geometry like this. Okay. So, the maximum temperature is attained at the interface, little less away from the fusion from the interface like this. So, if we measure, if we see at the interface peak temperature is high, then it is decreasing away from the like this, okay, away from the interface, and the same thing will be happening for other side also. So, since the maximum temperature is attained at the interface, so the maximum reversion will be happening and maximum coarsening will be happening at the interface, while away it will be happening less. So, here we will be getting the hardness distribution of this kind. So, this pH metals will be showing the minimum hardness at the interface and maximum hard and the maximum hardness will be there at the location, will be at the location away from the interface, especially the zone which is unaffected from the heat or the deformation. But if we talk of the transformation hardening metals or work hardening metals, in case of the work hardening metals, what we will see that the hardness is maximum at the center. Why? Because the plastic deformation will help to increase the hardness. Same way the transformation hardening metals like the steels, when they are subjected to the solid state joining like friction welding, at the interface higher temperature will be resulting in the martensitic transformation, followed by the higher temperature will be resulting in the transformation of the soft phases into the austenite, followed by the rapid cooling, that in turn will be resulting in the martensitic transformation at the center. Okay. So, higher hardness of the work hardening metals is due to the plastic deformation, and the weakening of the metal at the interface in the pH metals is due to the reversion. Okay. Now, if we try to compare the joining with regard to the fusion versus solid state joining process for the work hardening metals, since the work hardening metals, if we talk of the fusion welding and pH metals, no. So, both are adversely affected by the heat supplied and the peak temperature and soaking time. These are the two most important aspects that affect the work hardening and the precipitation hardening metals. So, if we see in fusion welding, since the heat applied is much more for realizing the melting followed by solidification, and therefore, we get the much wider heat affected zone. So, the zone which is affected during the fusion welding of pH and work hardening metal, this is very wide. Okay, and and higher heat, higher peak temperature, greater soaking time will result in the severe recovery, recrystallization and excessive grain growth. Therefore, we will find a significant loss of hardness and strength. Okay, like this, and therefore, severe HZ softening will be observed during the fusion welding, especially the heat affected zone of both work hardening and the pH metals. Okay. But on the other hand, if we talk of the solid state joining will be causing the two things. One, maybe micro or macroscopic plastic deformation, this is one, coupled with the heat generation, because in any case little heat will be generated, but the kind of heat that is generated or supplied, that is very less as compared to that of the fusion welding. And therefore, what we find in case of the work hardening metals, when solid state joining process is applied, plastic deformation will be helping to increase the hardness and strength due to the work hardening. Okay. That is the case of the work hardening metals. But in case of the precipitation hardening metals, if the work hardening behavior is not significant and the heat generation is much higher, then this will be causing little recovery without much gain due to the work hardening. But since the heat input is less, so what will be happening? Our HZ will be narrow. Okay. So, our HZ may be very narrow in due to the lesser heat affected zone, and due to the lesser heat supplied, the recovery will be recovery may not be complete, but it will be less, relatively less recovery, less recrystallization and less grain growth. Okay. And because of all these factors, what will be happening, like our the jet softening is limited, it will be there, but it will be limited. Why? Because there limited reversion, limited recovery, limited grain growth. So, in case of the pH metals, in case of the pH metals, if heat supplied is less, so it will reduce the reversion, it will reduce the grain growth. Okay. And both these factors in turn will reduce the extent of HZ softening that will be happening. So, in a way, the solid state joining is better, but we have to see that whether it is work hardening or precipitation hardening metal, that should have the enough ductility. Okay. So, that whatever microscopic or macroscopic plastic deformation that is needed during the solid state joining, that can be realized. Now, I will summarize this presentation. In this presentation, basically I have talked about the how the work hardening or precipitation hardening metals gain their strength and what happens to the change in structure and properties of these metals when the heat is supplied during the welding, and accordingly what kind of the structure and properties are realized in the heat affected zone. Thank you for your attention.